Welcome back to another video. I am Kadisha Crony, and I am the lead scientist here at DOA International Education. This is our first video in the Principles of Chemistry 1 series, and today we're looking at states of matter. Let's get right into it. My objectives for today's video include the introduction of the particulate theory of matter. I'll also be demonstrating evidence that supports the particulate theory of matter. I'll be identifying and differentiating between the three states of matter. And lastly, I will be describing the differences in energy and particle arrangement between the three states of matter. Let's start with the particulate theory of matter. What is it? Well, the particulate theory of matter is a proposition that entails the characteristics and actions of matter. What am I saying here? How matter behaves. Recall, matter is anything that has mass and takes up space. What are some examples of matter? Air, water, rocks. What else? Buildings, tables, you name it. Matter can also be categorized into what we call solid, liquid, and gas. Now, what are the postulates, or what I said before, the propositions of the particulate theory of matter? Well, the first one, all matter is made up of tiny particles called atoms or molecules. Now, these tiny particles are movable, right? We say they move in a random fashion. Now, there are also forces of attraction between the particles and external forces. One of the main important one, temperature affects the particles. Now, I am going to be testing these postulates, or I am going to be elaborating on some examples that really test if these postulates are true. The first postulate or proposition was that all matter is made up of tiny particles called atoms or molecules. Now, thankfully, back then in the scientific world, we had this British scientist called John Dalton. He studied the chemistry of the elements, and he theorized that matter was made up of tiny particles called atoms, which he also stated were indivisible, meaning the atoms cannot be broken down into anything. Later on, other scientists did more work and found out that it was indeed true. All matter was made up of tiny particles called atoms or molecules, but they also found additional information to conclude that the tiny particles called atoms, they were not indivisible, right? They could be broken down into protons, neutrons, and electrons. Later on, if you decide to do cave chemistry, you'll learn more about the major scientists in chemistry. Now, recall the second postulate or proposition was that tiny particles called atoms or molecules are movable, meaning that the particles, they can move around in a random fashion. How can we test if this is true? We can use two processes. We can use diffusion and osmosis. Now, diffusion is the movement of molecules or ions from where they are more concentrated, or where we would say there's a lot of these molecules, right, to where they are less concentrated, or we would say there's a small amount of these molecules. And these molecules move until we have an equilibrium, or what we'd say an equal distribution of the molecules or ions. All right, let's jump over to diffusion to see how these atoms or molecules move. Now, in my demonstration, here I have a chemical. It is called potassium permanganate. And the potassium permanganate here exists as crystals, solid crystals. Now, here I am showing my students that if I take a spatula full of potassium permanganate, KMnO4, and I place it in water, yes, it will diffuse, or what would say will move randomly in the liquid until it is evenly distributed, right? As you can see in the picture there, the first picture, I have a clear beaker of water, and then when I put the potassium permanganate crystals in it, the crystals evenly distribute throughout the beaker of water, and over time, look at my picture in the right there. Over time, you'll notice that the crystal diffuses evenly throughout the beaker, right? That is a perfect example of diffusion. Osmosis is the movement of solvent molecules or water molecules from a region of lower solute concentration to a region of higher solute concentration through a semi-permeable membrane. To demonstrate the movement of these solvent molecules, let's take a tour of my virtual lab. Stay tuned. Okay, so first thing, I'm going to peel the potato, and then I'm going to take the knife to make a cavity in the middle of the potato. Next, I'm going to place my potato in a dish with distilled water, and I'm going to add some salt, some Himalayan salt to the hollow cavity. I'm going to leave it for 2 hours. Let's see what will happen. Wow. So what are we seeing here? We're seeing that water traveled from the dish, which had a low amount solute, to the hollow cavity of the potato, which had lots of solutes or salt molecules through a semi-permeable membrane, which was the potato. And this therefore summarizes the process of osmosis. Now I want to see you trying this experiment at home. Now, the third postulate was that external forces such as temperature affects the particles. To demonstrate this, I now invite you to follow me to my virtual lab where I will show you how diffusion is increased with the introduction of a hot temperature versus a cold one. So what do we notice here? We notice that with the introduction of hot boiling water, which symbolizes a greater temperature, the dye diffuse at a faster rate compared to the one in the cold medium. Now, finally, let's talk about states of matter. Now, matter can exist in 4 states. Recall we said that matter was anything that has mass and takes up space. Yes, it can exist in solids, liquids, gases, and I'm going to throw in a final one, plasma. Let's jump over to my smart board. Now, the first state of matter that I'll be looking at is solid. Now, what do you notice about the particles here in solids? You notice that the particles, they are tightly packed together, right? So there's limited space for particles to move. Should there be any diffusion occurring, right? The space is minimal for them to move. Now, importantly, because the particles are so packed together, they are stronger intermolecular attraction, right? So in order to convert solids to another state, it would require a greater amount of energy. Now, because the particles are so tightly packed together, we say solids have a fixed shape and a fixed volume and has a high density. What are some examples of solids? Ice, sugar cube, blocks. Now let's jump over to the next state of matter. This is liquids. What do you notice? The first thing that you should notice is that there are more spaces, right? So there's an adequate amount of space for particles to move. So should there be processes like diffusion and osmosis, right, the rate would be greater than that of solids. They too have strong intermolecular attractions too, and it is important for you to note that the shape of liquids varies, right? We say liquids, they take the shape of their container because the particles can move around freely than they can in a solid. What are some examples of liquids? Water, right? The greatest solvent, milk, and blood. Let's move over into gases. What's the first thing that stands out to you for the gas state? Right? The particles are more far apart from each other, or what we would say, particles in a gas are separated by a much larger space than in liquids and solids. So, of course, diffusion is going to be super high in gases, right? Imagine standing at one location in your room and you spray some perfume. In minutes or seconds, the person standing in your hallway will start to smell the perfume, right? Because the particles are super free to move, right? Now, because the particles are so far apart from each other, there are no intermolecular attractions between them. And unlike liquids, which take the shape of their containers, for gases will fill whatever containers they are in, right? The particles are moving in all sorts of direction. They're spread out through the container. So they won't take the shape of the container, but they just spread out through it, no matter what volume or shape the container has, right? What are some examples of gases? You might ask. Oxygen gas, carbon dioxide gas, helium, nitrogen, you name it. Lastly, plasma. Now, the particles here, they are arranged in that they are electrons, ions, and they are attracted to electric and magnetic fields, right? And of course, you must expect that the energy of these particles are very high. And what are some examples of plasma? Lightning are the stars in our galaxy. Now, finally, let's talk about changing states of matter. This means how can one state change to another? Well, we have here freezing, melting, evaporation, condensation, sublimation, and deposition. Freezing occurs when a liquid state is changed to a solid state. Give me an example of freezing. Awesome, right? We put liquid water into our ice cube molder, and then when we put it in the freezer, guess what? It changed to solid ice cubes. Now, these ice cubes can melt or change from solid to liquid if we apply heat to them, and this is called melting. Now, evaporation occurs when there's a change of state from liquid to gas. For example, at school, there's a large puddle of water, right? And because of the hot temperature in our environment, that liquid will change to gas. Condensation now is when the gas begins to cool, right? Say in evaporation, the gas rises into a cloud and then the environment changes. Now it becomes more cooler, right? We'll have a change of state where this same gas begins to cool and form liquid droplets of rain. That's a good example of condensation. Sublimation occurs when there's a change of state from solid to gas, and deposition from gas to solid. Thanks so much for watching this video. Stay tuned for part 2, where I'll be talking about heating and cooling curves. Stay tuned and remember, hard work is the key to success. Bye.